Swayam Prabha. Digital India. Educated India.
Today's lecture is actually about this guy, the absolute scale of temperature. But we'll take a few steps to get to that point. And those are the steps which are listed on top. So last class we had Carnot Theorem and had a small proof of it. And I will continue with that idea again. And let me write this down once. To remind ourselves of Carnot Theorem, the main idea was eta irreversible is less than or equal to eta reversible. What we showed was that if we assume the other way round, an irreversible engine having a higher efficiency, it leads to a contradiction of second law. We will exactly. The equality, his point is the equality will hold when both the engines are reversible, and that is what this is. So you know this next point also. Corollary to Carnot's theorem is that if two engines are reversible, they will have the same efficiency. So what's so great about it? We'll see that. Okay, so let me write the statement again to make sure that we what we just said. I'm going to write it clearly on the board, and if we follow it, all reversible heat engines operating between the same source and sink, but we'll say it more precise, the same fixed temperature source and the same fixed temperature sink all those reversible engines have identical efficiencies. Okay. The way we showed Carnot theorem, I'll draw a quick sketch here and we'll use that again on the other side. We said if we have a source and a sink, and we have a reversible engine ER, Q1R, Q2R and WR, and we have an irreversible engine EI, Q1I, Q2I and WI. You can place the arrows appropriately. We can invert each step of the reversible engine to get an equivalent, exactly equivalent pump. We call that P sub R, Q1R, WR, Q2R, and now let me place the arrows to show the directions. And the argument was that if we can make the pump operate at a speed which will exactly match, so that the heat delivered will exactly match the heat taken up by the irreversible engine. Then we'll combine these two to make a new engine which will have a positive work output, because this work output is greater now, we are saying, than the work input of the pump. The top reservoir is eliminated, and the bottom reservoir gives us the net heat, which is Q2R minus Q2I. So you can refer to your notes last time. So that was the idea. We said that if eta I is greater than eta R, this contradicts second law. I'm going to extend this argument now today to show this, the corollary, which is actually fairly straightforward, as you have already, you can probably guess. And I'm going to go a little fast on this, so stop me if you have any questions. So I'm going to place two engines, A and B, EA, EB, taking Q1A, rejecting Q2A and WA work output, and the second engine has Q1B, Q2B and WB. Now we are saying both are reversible. So let's invert the one on the right to make it into a pump. And if you allow me to erase and do this in the same picture, I would invert the direction of the arrows, keeping the magnitude the same. And to complete the picture, let's show the cycle around E and P. And if we follow the same argument that we did last time, okay, let's start, get to that, what he said. So if we follow the same argument, we start with the one that we convert into pump, we say is less efficient. That's what he probably meant. So we say eta B is less than eta A. We start with this, convert this into a pump, and then do the same process to construct an engine which will violate second law. Can you see this, or do you want me to go through the steps? Okay. Let me quickly, without writing, let me do this. If we say A is more efficient than B, then WA is larger than WB for the same amount of heat taken up by the two engines. When I convert it to pump, again keeping these Q1A and Q1B constant, WB is less than WA. So when we make a combined engine, then the net work output WA minus WB so this gives me a work output of WA minus WB, which is greater than 0, because of assuming A being more efficient generates more work, and we eliminate the top source by connecting the heat delivered by pump B into putting it into engine A, and then we say there's a net heat interaction with one reservoir, the lower one, which we initially called a sink. So and that is the heat taken up is Q2A minus Q2B. That's also positive. You can show that with these arguments. And we did that for EAR and EI last time. I'm just using the same thing for A and B. Fair enough, right? So this essentially gives us that eta A should be less than or equal to eta B. exactly same arguments, but all I'm saying is that I invert this engine B and get that, and now I'm going to apply the same procedure by inverting A and keeping engine B as same. Okay, let me do it quickly again and see if it makes sense. Let me draw the diagram here. Again, we start with the same picture, initial. So we say Q1B, Q2B, WB, Q1A, Q2A, WA. Fine. And now I'm going to invert the first one into a pump. We are able to do this because we are able to do invert any of them because both are reversible. So I'm using the fact that we are dealing with all reversible engines now, instead of Carnot theorem initially, which had a comparison of reversible and irreversible. Now I'm dealing with both are reversible. If you wish, I can write that. Both EA and EB reversible. So I can invert any of them into a pump and get the exactly same Q's and W's for that engine. If one of them was irreversible, we couldn't do that. That was the argument that we followed last time. So if we now, once we have inverted into a pump, I'm drawing heat from below and pumping it to top. WA is in work input, and engine B is as usual Q1B taken from source, Q2B rejected, and work WB is an output. For this, if we start with eta B greater than eta A, if, then again we apply the same argument, make a new engine which is a combination of the two, and show that it will have, if this is true, eta B is greater than eta A, then it will have a non-zero work output while taking up heat only from one reservoir and not rejecting any of it, converting all of that into heat, into work. So this will contradict again second law, which implies that eta B can only be greater than or equal to eta A, and that takes us to what you were saying. If you cannot find it on the phone, you can find it here on the board. Fine. The arguments are also important, how we get there, even if it's almost, finally what we get seems intuitive, right? But it was not so 200 years back. Alright, so what we are getting is exactly what we said at the top, saying only way this is possible, only way that you can satisfy both this and this is by the equality. Now imagine that one of the engines, engine A, is our ideal gas filled in a piston cylinder. First example we took for Carnot engine. It goes through the 4 steps of isothermal heat addition and then expansion, adiabatic expansion, and again heat rejection, and so on and so forth. We had the cylinder that we placed on a hot source and a cold sink and all that stuff. Let the piston move and do the work. That is one of the engines. And the second one, let's say, is our water and steam combination, where we evaporate water to pick up heat, and then we take it to a higher pressure and condense the steam to reject heat. Two very different engines with two different material or gases or what liquid gas combination. The working fluid is entirely different. The heat pickup and rejection processes are different. But as long as they operate within the same source and sink, they are bound to have the same efficiency. Question? Did I make a mistake? Yeah, right. Thanks. Essentially, I ended up writing the same thing. Eta B less than or equal to. Okay, great. Okay. Now, the next question will come to you. Pay attention. Because he thinks he knows everything. Maybe he does. But okay. So, does that make sense? Two entirely different engines with any different working fluid, any different steps of heat addition and heat rejection, they will come back and say that efficiency, as long as they are working between the two same reservoirs, have to be same. They can take up different amounts of heat, generate different amounts of work, reject very different amounts of Q2, but the ratios will match up. That's all we are saying. Yes. Okay. So, what I said was, if we have, let's say, water and steam, the heat absorption process is the evaporation of water to steam. Whereas if it's an ideal gas, we are not going to, it's already a gas, we can't evaporate it. We just do that expansion, look up your notes and we say, we let the piston move, the gas cool down a little bit and heat comes in, and again the gas expands. So it's an expansion process where we're adding heat and keeping the temperature constant. If you think about work and in a piston cylinder, the work is by pushing the piston, right? In a different engine, it can be a turbine work. You have turbines getting rotated by the gas or the steam coming in, steam turbine, let's say. So the work interaction, the machines can be different. How we extract work can be different, or how we extract or input or extract heat can be different, but the ratios will be same. Ratios in the form of the efficiency, and this we write as WA over Q1A, and this one is WB over Q1B. Any other question? Yeah. If it is irreversible, right, equality should not hold if it is irreversible. Only for reversible it will be. Yeah. Okay. Now, the fact that that this efficiency in terms of work and heat depends only on the temperatures of the source and sink is used to develop what we probably already have heard of as called the absolute temperature scale. So to do that, we'll do again a short derivation to make the case. We have an engine E1 taking up Q1, rejecting Q2 and generating work W1. Let's call this sink. So this is a reservoir at T1 and this is at T2, for which we use the same efficiency. Let's do it here. Efficiency 1 equal to W1 over Q1 and W1 equal to Q1 minus Q2. Okay? I'm using my same block of engine and pump to do all these different things. Remember, second law we defined these two basic components that we'll keep using and reusing. Then we get, we have one more engine which operates between T2 taking up heat Q2, engine E2 rejecting heat Q3, and this is a reservoir at T3. The work output is W2. And we write this eta 2 is W2 over Q2, and W2 is Q2 minus Q3. Agreed? What to do next? Which you always do. Yes? Remove T2, fair enough. And then do what? You combine the two engines to make a new one. Right? So, as you said, remove T2, because T2 is not quite required. We can straight put in the heat coming out of the first engine directly into the second one, but we still say that it's happening at a temperature of T2. The temperature will be important. And then we take this whole thing up, make a new engine, the new engine will again satisfy the same steps that we used to define a Carnot engine, because all these steps are reversible. Imagine each of these had reversible steps. So whatever is happening in between, the two engines is getting cancelled, but the remaining steps are still reversible, isothermal and adiabatic, the way we defined it. So new engine also is a Carnot engine. We can write the same thing here. Eta 3 for engine 3 is W1 plus W2 over Q1, right? Thanks. And W1 plus W2, which you can probably see from here and here, equal to Q1 minus Q3. Okay, up to here is straightforward. And then I'm going to make a few changes to this, which also still we are aware of. I'm going to write this as 1 minus Q2 over Q1. Eta 2 is 1 minus Q3 over Q2. And eta 3, the combined one, is 1 minus Q3 over Q1. And put in one more thing here by saying that, in fact, I'm going to use it, let's use it here. Okay, let's do it separately. We say that efficiency of a Carnot engine, if it is operating between two, let's say the first one, Q2 over Q1, this efficiency can be a function of T1 and T2 alone. For all reversible Carnot engines, the efficiency is a function, depends only on the source and sink temperature, does not depend on anything else. Any of the processes involved, any of the material involved does not depend on that. So mathematically I'm writing it eta as some function of T1 and T2. Agreed? And I'm going to change it a little bit and say, can I write Q1 over Q2 is some other function of T1 and T2. I've just manipulated the same thing. Move the 1 around and invert the ratio or whatever it is. If efficiency depends only on the temperature ratio of the temperatures, then the ratio of heat taken up and heat rejected has to be a function of only those. Fine? So then, Q1 over Q2 is a function, let me rewrite it here, T1 comma T2. Q2 over Q3 is a function of T2 and T3. Those are temperatures between which the second engine is working. Again, it does not depend on what kind of engine we put in. As long as it's reversible and it's a Carnot engine, that relation is bound to be valid. And again, and the third time apply the same, we say Q1 over Q3 T1 comma T3. And now I'm going to combine Q1 over Q2 equal to Q1 over Q3 divided by Q2 over Q3. The left hand side is f of T1 comma T2. The right hand side is f of T1 comma T3 divided by f of T2 comma T3. And here's a problem. The left hand side is independent of T3. Yes. Yeah.
So, won't that ratio depend on the temperature of the source and sink as well as the temperature at which the engine is working?
The temperature at which an engine has. The question is, would the efficiency or the ratio of heat, you mean this one, right? The ratio of heat taken up and heat rejected, would it not depend on T1, T2, which are source and sink temperature, as well as the temperature at which the engine is working? So, what is the temperature at which the engine is working?
There are many temperatures at which the engine is working in a circle.
Yeah.
So, there is no specific
There is no specific temperature that it works. And only thing that defines it has to work between those two levels. One isothermal process of heat addition, T1, other one T2, between that work interaction. And between the two work interactions cannot have any heat transfer. Can it? No, because I know, but why? If they were not adiabatic, what would happen? There would be additional source and sink. Your whole basic idea of you have source at constant temperature T1 is not valid anymore. You are taking up heat at another process also at a different temperature. The whole argument falls apart. So you have to specify temperature of sink, source and sink, and operate it between those two. The rest two are adiabatic process. So there is no other temperature. It has temperatures, but there is nothing to characterize it. All temperatures are taken between T1 and T2, as he said. There is no specific temperature. Okay. So the argument here is that if left hand side is independent of T3, right hand side should also be independent of T3 for all these arguments and theorems and corollaries to be valid. So T3 should drop out. And that is possible if the f function is ratio of two functions, ratio of two of this form. It can be any function phi, but as long as it's the ratio of these two, it is bound to drop out. The right hand side you can put phi, you can replace the numerator by phi of T1 divided by phi of T3, and the denominator by phi of T2 divided by phi of T3, T3 part cancel out. It's fairly obvious. So where is the new temperature scale? Where is our absolute temperature scale now in all this thing? Yes. The repeat is, we did all these things putting a heading of absolute temperature scale. We are getting to the absolute temperature scale. So where is it in this whole thing? Okay. Okay. You have not done this course before, right? The textbook exactly says the same thing what you say. He probably read it on his phone. But it doesn't matter. What he's saying is right, but I'm going to put it slightly differently. Phi of T1 can be any function, and he said, why don't we take the simplest possible function? Right? Phi of T is equal to T. Let me write it slightly differently, which may actually, which part do I erase? Maybe here. Q1 over Q2 is phi of T1 over phi of T2. I'm going to write that phi is any symbol. I'm going to use a different symbol. T prime is my function of T1, T prime of T2. So let's write this. Phi is any function of T, and I'm saying T prime is any function of T. It's just a symbol. Agreed? Nothing special I did. Fair enough? And then I'm going to say that if the value of T1, T prime, the function at T1, I call it as T1 prime, no problem. I pick the value of that function and call it T1 prime. T prime at T2, I call it T2 prime. Nothing wrong in that? If I do that, I'm writing this Q1 by Q2 as the ratio T1 prime by T2 prime. And my T1 prime and T2 prime are the temperatures in the new scale, which we'll call as absolute scale. It's a little tricky and not intuitive. But what we'll do is to derive these two scales of absolute temperature. Things will get a little more clear when we do that. Kelvin scale and Rankine scale. Yes?
So you're saying T dash is actually a function that converts absolute scale temperature to another scale.
It's the other way around. T prime, T dash is a function that converts a regular scale to an absolute scale. Right, that's what I'm saying. So T prime is essentially the absolute scale temperature. Okay. So this step is important, and let me box it. The main important thing is that in this scale, if you're able to measure Q1 and Q2 heat transfers, then again it does not depend on what fluid you used. Whether you used ideal gas or you used anything, as long as you have an engine running which takes up Q1 and Q2, you can measure that and get the ratio. You have the ratio of temperatures of the absolute scale without or independent of what is the working fluid inside. We'll see the importance slowly and both historically and how it makes a difference to us now. But let me derive or work out these two scales first. Okay. So if we have if you want to develop a scale now, we take a source and a sink, which are at temperatures which we are very comfortable with. Okay, so let's say T2, the lower temperature, is 0 degrees Celsius. T1 is 100 degrees Celsius. And then we are able to operate a heat engine, a Carnot engine, which takes Q1, Q2 and W output. If you are able to measure the heat input, the work output, and take a difference and get Q2 or whichever way you want to do, and people have done it in some very sophisticated ways, what you get is Q2 over Q1 equal to, you can measure this value, and there's a numerical value that comes up, is 0.732. And if you have this is equal to T2 prime by T1 prime bar dash, whichever one you call it. That decides the ratio of the two temperatures. If these two are the fixed points on a scale, on a new temperature scale, which you say I would place a marker at melting point of ice, water, and another marker on your temperature scale. Let's put it this way. I am making a new scale. Let's say we have 100 degrees here. This is a centigrade scale, and we have 0 degrees here. The new scale, I am going to place markers at these two. This is my T2 prime, T2 dash, and this is my T1 dash. And by doing this experiment, I can get a value for the ratio of temperatures just by second law. Then I would say that, okay, now what? I need one more equation, one more relation to fix the temperatures. So I will say that, what if I want 100 degrees, 100 subdivisions between these two markers? Because we have exactly 100 divisions here. I want the same number of divisions here. So that makes this T1 prime minus T2 prime equal to 100. And now it's trivial to calculate T1 prime and T2 prime, and if you do so, you'll get, yeah. So T1 prime times 1 minus 0.732 equal to 100, and if you have pull out your calculator and check this out, it will be 373. Sorry, T1 prime is 373 point some 15 value. T2 prime is 273.15. The unit that we place is Kelvin. So we say that Kelvin scale is the absolute temperature scale corresponding to the Celsius. We started with Celsius scale and we got this. The other one, the Rankine scale, is exactly same process but starting with Fahrenheit scale. It just so happens that in the West, if you go to any US, UK, you will see that Fahrenheit scale is far more common even in day to day. They report temperature, outside temperature in a cold winter day with in Fahrenheit, 0 degree Fahrenheit. Doesn't feel so bad. It's already minus 20 degrees centigrade. Okay, so here is my new scale. 273.15, if you want 373, and here is my Kelvin scale. If you repeat this procedure with the Fahrenheit scale, remember that this part is independent of what scale, what material you use. Yes. That is experimentally obtained. Good question. Yes. The experiment is not possible. Absolutely true. So the whole argument is about that if you operate a Carnot engine and measure its Q1 and Q2 and W, then you can do this. But Carnot engine is practically impossible. So what people have tried is to get as close as possible to a Carnot engine, but you cannot do so. So this number is, if you follow this procedure, even though I described it in this way, the procedure, that number that you get is not very accurate. So when they do experiments in the lab, they actually follow some other procedure which is equivalent to a Carnot engine. We can't go into those; they're more advanced topics. But they use the principle of Carnot engine and second law and obtain what is equivalent to the ratio of heats and get this number. So we have to follow. If you follow this number and assume that if it was possible, we will get the same number.
From this logic, how can we see that in absolute scale we cannot go below 0?
We'll come to that. They'll probably go to the next lecture, but that's the. So he said, how do we see from this logic that we cannot go below 0 in absolute scale? We'll see that when we extend this idea further to 0 degrees. Okay. Let me just put down the numbers for the Fahrenheit scale and complete this topic. For Fahrenheit scale, we have this is equal to 32 degrees Fahrenheit, and boiling point of water is 212 degree Fahrenheit. The difference between T1 and T2 is 180 degrees. So T1 prime is 180 divided by 1 minus 0.732, which comes out to be 462, I think. No, 672. Please check these numbers if you have a calculator. 672 degree Rankine. And T2 prime is 672 minus 180. That is probably 450 something. 490. 492. All right. So finally, let me write this here, that Kelvin scale is centigrade plus 273.15 and Rankine scale is Fahrenheit plus 460, if I am not wrong, 460. Okay, let me take up the absolute zero and other arguments in the next class, but we have a few minutes left, and it was a question came up at the end of last class saying that in this argument of Carnot theorem, what if we start with other way round? Remember, somebody had asked this question? Yes. Did you figure out the answer? Okay, let me put the question to everybody else. So we said if we start with eta I greater than eta r, we end up contradicting second law. But what if we start with the other way around? What if we say that eta r was greater than eta I? Do we still get a contradiction? What happens? Exactly, but what do we get if we follow this? We'll get net heat input and we'll get net heat output. We can still eliminate the source. Yeah. So all of these things will become opposite, right? So if we do that, the argument we have to do is all of these will become opposite. So we'll have it here. In this case, we had a net work output while we got the same amount of heat coming in from a single source, and we said that violates second law. If we start with the opposite argument, we'll get a net work input, an equal amount of heat going back to this source. And does that contradict second law? No, because of Joule. Joule did exactly the same thing. He had this parallel wheel experiment where work was coming in and that was converted into heat, and it found that the two are exactly the same. So that is nothing but first law experiment, Joule's experiment. Okay, I think we'll stop here today for a few minutes. If you have any more questions, you can stop by.